Welcome. So we're going to jump back into supplementary material on geometric thinking, and in particular lines and planes. So I'm going to do some problems, and I hope you do the same. Of course, these are not in the workbook, but they're easy enough, and I really hope you follow along. Okay, so question 2. Find the vector, parametric, and symmetric equations for the line through the points. So we've got a P, which is 1, 3, 2, and a point Q, which is -4, 3, 0. So the first thing we want to do is connect the two of these with a vector, and so let V be equal to the vector PQ. And so we compute that via Q minus P. And so that's -4 minus 1, comma 3 minus 3, comma 0 minus 2. So we've got -5, 0, minus 2. Okay, so this is our vector V. Now let's draw a picture while we're here. So P, we've got Q. This is the vector V. Okay, and then we might have an origin here. And so the vector PQ tells you how to get from P to Q. But if you connect this, with a bigger line, you've got a line that is parallel to PQ. Okay, now to represent the vector equation of the line, so let's write vector. So that looks like R equals, now we just take, say OP for example. We need a point that we know is on the line, so just take that for example, but we could take OQ as our vector. And so then we add the vector V times some parameter t, where t is any real number. Okay, so here we have from O to P, and then we're adding this vector plus some scalar multiple of this vector. And so if the scalar multiple is just fairly small, right, so that we might have this, for example, being R. Well, from O to R, that takes us here, and so that also gives us a point. But let's simplify this. So OP is P minus O, and then plus this vector times T. So -5, 0, minus 2 times T. So P minus the origin is just this. So we have 1, 3, 2 plus -5, 0, minus 2 times T. Okay, and now this completes our description of the vector version or vector equation of the line connecting P and Q. Okay, now the parametric equation, well, consider this. If we have, so let uppercase R be any point on the line, and let's call that X, Y, Z. So let it be on the line. And by the line, I mean the line that connects P and Q. And let lowercase r be equal to the origin to the point R. Okay, so if this here is the point R, then lowercase r, the vector, tells you how to get from the origin to the point R. So we're calling this X, Y, Z, and combining this, that is 1 minus 5t comma 3, and then 2 minus 2t. Again, t is any real number. And this says t is an element of the set of real numbers. Okay, so we're almost at the parametric equation of the line. This is parametric because we've represented this line being the collection of points in terms of a parameter t. But to put this properly as a parametric equation of the line, these are usually known as x equals something, y equals something, z equals something. So let's write it that way. So we have x equals 1 minus 5t, we have y equals 3, and we have z equal to 2 minus 2t. So this system right here is parametric equation for the line, where t is any real number. Okay. Now again, how does that give you a point? Well, if I choose a t value, say t equals 0, then I get the point 132. I know that's on the line. Okay, let's ask the question. What parameter value gives us minus 430? Well, I would want this to be 0, so let's take t equals 1. So if t is equal to 1, then I get minus 430. Okay, so let's write that out. If t equals 0, we get 132, and if t is equal to 1, we get minus 430. But I could choose other points. For example, I could choose t as 1/2, and so on and so on. If t equals 2, we get, let's see, 1 minus 10 is minus 9, 3, and then 2 minus 4 is minus 2. So this describes a collection of points. All right, so next let's go for the symmetric equation. So to write the symmetric equation of the line, well, what we want to do is take these equations and eliminate t from them. So we'll write 5t is equal to 1 minus x, and then solving that for t, we've got t equals 1 minus x all over 5. Okay, so next let's do the same thing with this. So from z equals 2 minus 2t, we have 2t equals 2 minus z. Divide throughout by 2, and we have t is equal to 2 minus z all over 2. So now these two t are supposed to be the same, right? And so we can combine these two equations and say 1 minus x all over 5 is equal to 2 minus z all over 2, semicolon, and y is equal to 3. Okay, as it is there. So this is the symmetric equation of the line, if I remember the wording right. Okay, let's move on to the next question. Number 3. So we've got two lines. L1 says x is equal to minus 6t, y is equal to 1 plus 9t, z is equal to minus 3t. Okay, so this is a parametric equation of the line L1. L2 colon is the lines, or line, x equal 1 plus 2s, y is equal to 4 minus 3s, and z is equal to s. All right, now the question is, determine whether they're parallel, skew, or intersect. So these are lines in 3 dimensions, so they don't have to intersect. And they don't have to be parallel. They could be what we call skew. So I'll show you with my two pens here. So take these two, right? So as lines, these in 3D, they do not intersect. So you try this with a pair of pens too, or if you If you feel like it, get some string out and a couple of mates and pull string taut between, you need 4 people, including yourself, to demonstrate this. Okay, so here's an example of skew lines, right? Now, here is an example of parallel lines. Okay, but here is an example of intersecting lines, right? So it's rather unusual for 2 lines in 3D to intersect, unlike for lines in 2D. All right, so the question is, are these parallel, skew, or intersecting? So let's assume that they intersect and see what happens. Okay, so if they intersect, then the x-coordinates would be equal. So then minus 6t would be equal to 1 plus 2s, and 1 plus 9t would be equal to 4 minus 3s, and minus 3t would be equal to s. Okay, so we've got 3 equations and 2 unknowns, and so we want to solve for s and t using these 3 equations simultaneously, and to see whether that's consistent or meaningful. So let's have a look. Now, from the third equation, we clearly have s is equal to minus 3t, so we can substitute that into the other 2 equations and write everything in terms of t. So this system gives another system, so let's write that here. Minus 6t is equal to 1 plus 2 in brackets minus 3t. Okay, now if we do the same substitution in the second equation, we have 1 plus 9t is 4 minus 3 times minus 3t. Okay, so expanding and collecting like terms. So this system says then minus 6t is equal to 1 minus 6t. And the system below says 1 plus 9t is equal to 4 plus 9t. Now you can see that we have the same t term on left and right. So this says that 0 is equal to 1. And this one says that 1 is equal to 4. That is a contradiction, right? Because 0 and 1 are not equal, 1 and 4 are not equal. Sometimes we just put a C exclamation to say that this is a contradiction. Righto. Okay, so now that we have a contradiction, what did we contradict? We contradict the assumption that they intersect. So the lines do not intersect. So if they don't intersect, then they must be either skew or parallel. Okay, so let's have a look at which one it is. So to see this, let's consider the vector equations of these 2 lines. So L1 in vector form is r equals 0, 1, 0 plus minus 6, 9, minus 3 times t. And L2 is the vector r equals 1, 4, 0 plus 2 minus 3, 1 times s. Okay, so vectors parallel to these lines are given by this and this. So L1 is parallel to the vector minus 6, 9, minus 3. L2 is parallel to the vector 2 minus 3, 1, but these 2 are multiples of one another. So minus 6, 9, minus 3 is equal to minus 3 times 2 minus 3, 1. So the 2 vectors, this and this, are parallel, so that means that the 2 lines, L1 and L2, are parallel. So L1 and L2 are parallel. Something like that. Okay, let's have a look at question 4. Find the point of intersection of the two lines, or sorry, of the line in a plane. Okay, so let's write this: x equals 3 minus t, y equals 2 plus t, z is 5t. So here's our line, and then we've got a plane, x minus y plus 2z is 9. All right, so find the point of intersection. Let's draw a picture. Okay, so here's our plane. Then we've got a line. Here's our intersection. Let's call that the point P. So to find this, what we want to do is sub x, y, z into this right here, and then solve for the parameter that for which those two things agree. Okay, so the strategy here is solve for t after substitution. Okay, so let's sub in. So we've got 3 minus t for x. Then we're subtracting y, so 2 plus t, and then plus 2 times z, which is 5t, and this is equal to 9. Okay, so we can solve for that parameter and then use the parameter in here to find the point. So expanding this, we've got 3 minus t minus 2 minus t plus 10t is 9. Okay, 10 minus t is 8t. So 8t, now 3 minus 2 is 1. So 8t is equal to 9 minus 1. And so that is 8. Dividing throughout by 8, we have t is equal to 1. So t equals 1 gives point of intersection. Okay, so let's use that in here to find what our point of intersection is. So we have x, y, z equal to 3 minus 1, comma 2 plus 1, comma 5 times 1, and this is 2, 3, 5. So the point of intersection of the line and the plane is the point 2, 3, 5. Now let's briefly check if it satisfies this. 2 minus 3 is minus 1, plus 2 times 5 is 10. 10 minus 1 is 9. So yes, it does satisfy the equation of the line and the plane. So it does intersect. That is the intersection of those two geometric entities. Okay. All right. Question 5. Find the angle between the planes. So we have plane 1, x plus y plus z equals 1, and plane 2 is x minus y plus z is 1. All right, so this plane has a normal vector that we can just read off of the coefficients. So n1 is the vector 1, 1, 1. And n2 is the vector 1, minus 1, 1. So if we find the angle between the two normal vectors, let's draw a picture. Okay, so here's a vector n1. And then, okay, so let's suppose we've got another plane. That intersects with this one, and it has a normal vector, so a vector perpendicular to it called n2. So n2 is this vector. Now if we find the angle between the two vectors, then we find the angle between the two planes. So we take the dot product, n1 dot n2 is equal to 1, 1, 1 dot 1 minus 1, 1, which is 1 times 1 plus 1 times minus 1 plus 1 times 1. And so we have 1 as our dot product. Okay, now the formula n1 dot n2 is the product of the norms of the two vectors times the cosine of the angle between them. And so let's call that theta. Now theta is the angle between the two vectors n1 and n2, but it's related to the angle between the two planes. All right, now the norm of n1 is the square root of 1 squared plus 1 squared plus 1 squared, so 3. Same for the norm of n2, it's also 3. And then we know that this dot product is 1. Okay, root 3 times root 3 is 3. So we have cos of theta is equal to 1/3. Okay, so now I'll open up my calculator in Mathematica and I'll type in arc cos for the inverse cosine, but you can get on the calculator and type in cos superscript minus 1 of 1/3. Okay, now this is going to give me that answer in radians. So theta is equal to 1.23, and it's approximately equal to radians. Okay, now this is less than pi on 2 radians, and that, remember, is 90 degrees. So since it's less than 90 degrees, it means that that coincides with the angle between the planes. So since theta is less than pi on 2 radians, the angle between two planes is also theta, approximately 1.23 radians. Okay, let's move on to the next problem. Question 6. Find parametric equations for the line of intersection of the planes. So we have a plane given in scalar form, and then we have another plane given in a type 2 vector form. Where lambda and mu are any real numbers. Now I feel like I should explain this description a little bit. So suppose we have a plane. Okay, it has a point, say 1, 0, 0 on it. Now think of this as a point. It's really a vector, but it's a vector from the origin to the point 1, 0, 0, which also describes a point. Okay, so we have that point 1, 0, 0, and then we have a vector, namely this vector 2 minus 1, 0 is parallel to the plane. This other vector 0, 1, minus 1 also parallel to the plane. So if you have two vectors that you know are parallel to the plane, and you have a point that you know is on the plane, then this is a vector equation of that plane. But if you just expand it out, you get a parametrization of the collection of points on the plane. So, incidentally, x, y, z equals 1 plus 2 lambda, 0 plus minus lambda, plus 1 times mu, so plus mu, and then 0 plus 0 lambda plus minus 1 times mu. Okay, so this gives us a parametric representation of the points on the plane. So let's write points on the plane can be obtained by choosing any two real numbers, lambda and mu. Okay, now back to the task. So these two planes intersect in a line, and so we've got to find a description of that line. Okay, so now that we've got this representation, let's take the x, the y, the z, and sub it in there and see what we have, because when we use these together, that represents the intersection of those two geometric objects. Okay, so substitution gives us, let's see, x is this, and then plus y is mu minus lambda, and then plus z minus mu. That adds up to 1, according to this, subbing these three in. Okay, so let's expand and simplify. So we have 1 plus 2 lambda minus lambda. Now the mu's vanish, mu minus mu is 0, so equals 1. Is that right? Okay, so sure. So this tells us then 2 lambda minus lambda is 1 lambda, so lambda equals 0. Seems a little bit too good to be true, but lambda equals 0 here gives us an intersection. All right, so if lambda is equal to 0, what is the line of intersection? What does it look like? So back to this right here, if we sub in lambda 0 there, so substitution of lambda equals 0 gives x, y, z equal to 1 comma mu comma minus mu. And so we can write this as, let's see, how should we write this? 1, 0, 0 plus 0, 1 minus 1 multiplied by mu. Because if we expand this out, then this is what we get. Okay, so what this tells us here is it tells us a point on the line of intersection, and it tells us a vector that is parallel to that line of intersection. Now let's look at what we're asked to give. Find parametric equations of the line of intersection. Okay, so if we want a parametric equation of the line of intersection, well, it's pretty much right here. We just have to set it out. X equals 1, y equals mu, and z equals minus mu. And this is our parametric equation of line of intersection. Okay, so that completes question 6. All right, now question 7 is a question on the distance between two planes. So let's have a look at this. Now I always encourage students to think geometrically and not just use a distance formula. So we've got 2x minus 3y plus z equals 4. And then we have 4x minus 6y plus 2z is equal to 3. All right, now these two are parallel. How do I know that? Because the normal vectors, so n1 is 2 minus 3, 1, is 1/2 of the other normal vector, 4 minus 6, 2, and so this one right here is the second normal vector, n2. All right, so these two have parallel normal vectors, so the planes are parallel. So given that, let's draw a picture. So we've got two parallel planes. What we need to do is find points on them that have a perpendicular line passing through. All right, so let's go ahead and do that. Now what we need to do is take the normal vector, so line perpendicular to the planes is the line. Well, we just take the normal vector and then we take a point that we know is on it. So for example, let's take the first equation. 2, 0, 0 gives us a point on that first plane. And then we take 2 minus 3, 1 times parameter t, where t is any real number. Okay, so this gives us a vector equation of the line perpendicular to both of these two equations passing through 2, 0. So we need to find, so if this, 2, 0, 0. So we've got 2, 0, 0. So this one right here, let's call that point P. Now we need to find the coordinates of the point P so that we can actually calculate a distance. All right, so the way we do this is we take, we've got x, y, z equals 2 plus 2 times t, comma, minus 3t, and then t. All right, so this, if we spread this out, writing three equations, that would be the parametric equation of that line. So now with that, we want to take that and sub into the second equation. Okay, so when we sub that into the second equation, we have 4 outside of 2 plus 2t minus 6 times minus 3t plus 2 times t. All of this adds up to 3. Okay, so expanding this, 8 plus 8t plus 18t plus 2t is 3. 18 and 2 is 20, plus another 8 is 28. So 28t gives us 3 minus 8 is minus 5. So the parameter that gives us p is t equals minus 5 over 28. Okay, so now I need to take this, sub it in there. So x, comma, y, comma, z is 2 plus 2 times minus 5 over 28. Okay, and then we've got minus 3 times minus 5 over 28 is 15 over 28. And then we've got minus 5 over 28, because that's just t. All right, so we need to simplify this fraction. So 2 times 28 is, let's see, is it 56? So 56 minus 10 is 46. So 46 on 28, 15 on 28, and minus 5 on 28. All right, so this is our point P, this one right here. So now what we have to do, what remains, is just calculate the distance between 2, 0, 0 and P. Right, and remember how to calculate that. That is the square root of the sum of the squares of the distances. So if I take this and subtract 2, right, as in the x coordinate of the first point, well, then I would get back minus 10 over 28, right? And so then I square that. Okay, so distance is equal to the square root of, so 10 over 28 squared is 100 over 28 squared, and then plus, now 15 over 28 minus 0 is just 15 over 28, so 15 squared is 225, and then 5 squared is 25. Okay, these are all over 28 squared. Okay, simplifying that, we can factor out the 1 on 28 squared out the front, and it is a perfect square. So we'll get 1 on 28 outside the front times the square root of, let's see, 225 plus 25 is 250, plus another 100 is 350. Okay, so there's our distance, if I've done the calculations right. But please check that yourself.